Thank you very much, Mr. Chairman. Before I forget it, I should say I'm giving this talk on behalf of Alexei Lomonosov, Pavel Pogoryov, and Peter Hess, and the main results I'm talking about, these are the experimental results, have been all obtained by my colleague Alexei Lomonosov. Well, here's a short outline of my talk. After a brief introduction to linear acoustic wedge waves, I would like to introduce nonlinearity to them by presenting you an evolution equation which contains an effective second-order nonlinearity. Then I would like to say a few words about the experimental technique, laser ultrasound, by which my colleague has demonstrated very strong nonlinear effects on the propagation of wedge waves. And then I would like to compare these results on nonlinear pulse evolution with theoretical simulations and predictions, analyze the Fourier spectra of these pulses, and sum up the talk. Well, wedge acoustic waves have been discovered in numerical calculations in 1972 independently by two different groups, one using the finite element method and the other one a method that we call the Laguerre function method. That means that the displacement of the mode of the wedge modes is expanded in a double series of Laguerre functions which are optimized to this geometry. These wedge acoustic waves are one-dimensionally guided waves in the sense that they are propagate along the tip of a wedge. They're plane wave-like for this propagation along the x1 direction here. K is the wave number, capital V the phase speed, and this capital U here is the modal field which is localized at this tip. In other words, it's decaying in the other two Cartesian directions. And these waves, yes, have interesting properties. First of all, they are non-diffractive, of course, because they're one-dimensionally guided waves. Then we have very low speeds of them, and at least in the ideal case, of an ideal wedge, there is no dispersion. They're non-dispersive. And you can achieve a high degree of localization at the tip, and these things strongly favor nonlinear effects, and these nonlinear effects influence these waves in a very specific way, as we shall see. Well, nonlinear bulk waves, longitudinal nonlinear bulk waves, are ordinarily described by the celebrated Burger's equation. The corresponding physical quantity is the strain du1 by dx1, u1 being the displacement in the propagation direction, the x1 direction, and x1 is this coordinate along this direction. And the Burger's equation looks like this here. Capital X is a stretched x1 coordinate. Tau is a retarded time, t minus x1 divided by the velocity of linear longitudinal waves, and this eta is a damping constant. Now, when Fourier transforming this quantity S with respect to this retarded time, the evolution equation looks like this here. This capital B is the Fourier transform of this S. You could call it a strain amplitude, which depends on wave number Q, and this stretched spatial coordinate X. And you have here this equation, this evolution equation. The nonlinearity is here split into upconversion term, frequency upconversion, that describes also higher harmonics, a generation of higher harmonics, and this frequency downconversion here. Now, when considering guided acoustic waves, one can do something similar, like, for example, surface acoustic waves or wedge acoustic waves. We can consider the Fourier transform of displacement gradient here. We choose U31. 3 is the coordinate normal to one of the surfaces, or here to the surface in case of surface waves. X1 is the propagation direction in both cases. You can Fourier transform this here, getting this Fourier transform B of Q and capital X, and using then well-established asymptotic methods, one can derive an evolution equation, nonlinear evolution equation for these B's here, which has the following form. It looks like this, and you see this equation contains on the right-hand side here a linear term representing damping or weak dispersion if it is present, and the nonlinear terms here become the nonlinear terms of the Burger's equation if this function g that appears here of k over q, the ratio of two wave numbers, would be equal to a real constant, and this exponent A here would be equal to 0. In fact, in the case that we describe bulk waves, we would get this Burger's equation. In the case of surface waves, we would have here such a function g, and the exponent A would be equal to 1. And in the case of wedge waves, these one-dimensionally guided waves, the exponent A would be equal to 2. And this has a consequence that these down conversion terms here, this down conversion term here is reduced in comparison to the effectiveness of the up conversion. So in other words, higher harmonic form faster, and nonlinear effects are enhanced in this way. This is demonstrated here in this little calculation of the growth of harmonics. You see here the growth of the second harmonic and third harmonic for wedge waves. These are the red curves. Surface waves, the dashed curves, and bulk waves, the dashed dotted curves. You see here for larger propagation distances, the growth of the higher harmonics is faster, much faster for wedge waves here. There is a conservation law, by the way, for the modular square of these strain amplitudes, which involves k to the minus a, and this explains why at the same time the fundamental is reduced lesser in the case of wedge waves than in the case of surface or bulk waves. Well, this function g that appears in this evolution equation can be calculated from the elastic moduli, nonlinear elastic moduli of the medium, and we have done this using this Laguerre function method, and it depends very much on the system's anisotropy. In fact, you need anisotropy in order to get this function g to be different from 0, the second order nonlinearity, which describes the strength of the second order nonlinearity. If you consider silicon and you have a geometry where the coordinate axes are parallel to the crystallographic axes, then, for example, this g would just be equal to 0. And the reason is that the midplane of the wedge is a reflection plane. In this geometry on the right-hand side, where the two surfaces are different here, 1, surface and 1, surface, this function g is has decent quantity. It is a complex function with a real and imaginary part, and it turns out that the pulse shapes that we shall be looking at, the acoustic pulse shapes, are mainly determined by its values at the argument 1/2. This function is defined for arguments between 0 and 1, and it's symmetric with respect to 1/2, and the value at 1/2 is particularly important for the pulse propagation. Now, a few words about the experimental technique, laser excitation, and what is done here is a laser pulse of high intensity is focused on a point near, on an excitation spot near the tip of the wedge, and Alexei Lomonosov uses a special technique that leads to particularly strong recoil, leading then to this, generating then this acoustic pulse at the edge, and the pulse shape is recorded at two different observation points here at the tip with a certain distance, in our case here about 13 millimeters, and the pulse shape changes due to nonlinearity from the first to the second observation point. The quantity measured is U31, the displacement gradient U31, which is the local slope of the surface. This is due to the fact that we use probe beam deflection here, so we deflect the laser beam at the sloped surface, measure the local slope. And these are now the experimental results. The pulse shape at the first probe spot here is the blue dashed curve here, which you see here, and the pulse shape at the second spot is the red curve. And you see here a very strong steepening of the wave front, at the same time a compression of the pulse and this spiking here. The black curve is the result of a simulation on the basis of the evolution equation that I've shown you with the strength, this function g, calculated from the elastic properties of silicon, and the initial condition of the simulation were the blue pulse. And you see one gets this steepening quite well reproduced. Here in this inset, you see simulation results with a synthetic initial pulse based off the so-called Gaussian pressure model, and the phenomena are basically the same. Well, in order to understand, we should keep in mind that this steepening with tendency to shock formation is a three-dimensional phenomenon. So you see here in a simulation the initial pulse shape. This is here, this line is here the tip of the wedge, and this is the direction on the surface on which we measure away from the tip. This is the initial pulse shape, and the pulse is of course localized at the tip because it's a guided wave. And as the pulse propagates, it evolves into such needle type thing here. We call this a guided shock wave that is forming here. In order to understand this nonlinear pulse evolution a little bit more, we have analyzed the Fourier spectra of these pulses. Here you see a log-log plot of the pulse shapes, Fourier spectra of the pulse shapes, result of a simulation over propagation distances beyond the shock formation distance in the undamped, the inviscid case. And what is interesting here is that at the high end of the frequency spectra, we see these straight lines which correspond to power law behavior. And this is, or the exponent of this power law is related to a formal solution of the inviscid version of the evolution equation that I've shown you. And it turns out that in the case of bulk waves, the Burgers equation, one knows of such a solution. It's easy to show that there is such a solution with exponent -1. This would correspond to this slope here. In the case of surface waves, it had been shown by Hunter for a slightly simplified evolution equation that there is such a solution with kappa equal to -2/3, and he did simulation showing that for small damping, such power law behavior can be shown from the sinusoidal initial conditions. Now we have found that in our evolution equation, we get a formal solution of this form here, power law of the wave number times a phase factor. And the exponent is equal to -1/3, whereas the phase factor is given by this integral here, which depends on the material properties. So the phase factor depends on the material properties. The exponent kappa is independent of them. And when looking at the slope of this curve here, we find that the result is -0.37, which is very close to this -1/3 here. With this, I would like to conclude my talk and summarize. I have shown you that wedge acoustic waves are non-diffractive, non-dispersive, which favors nonlinear effect, and such strong nonlinear effects have been demonstrated in experiments by Alexei Lomonosov with his laser ultrasound technique. And the prerequisite of these phenomena are, first of all, anisotropy. We need anisotropy to have decent second-order nonlinearity. The dispersion and attenuation have to be small. That is achieved by good quality tips, and attenuation in acoustic is small enough. And we need large strains, which are achieved by laser excitation. And we have analyzed the Fourier spectra, shown that this power law appears. With this, I would like to conclude, and thank you for your attention.